Welcome to Pre-Calculus. Today we will investigate writing and graphing inverse trigonometric functions. We'll take a look at 3 total examples. Our first example is one of our basic trigonometric functions, y equals sine of theta. I have 2 tasks. I essentially want to first write the inverse function's equation, and then once I've got that equation, I want to graph the inverse function. So we'll start off with that first task. Let's take y equals sine of theta and write its inverse. So as with any inverse, the first step I'm going to do is I'm going to switch my variables, my independent and my dependent variable. So here that's going to involve theta and y. So as I switch those, what I'll have next is theta equals sine of y. And that is the inverse function to sine of theta. Now, for me to be able to graph that inverse, I want to, at that point, solve it for y. So I see that I just have one step here in this function. I need to create a little room here. So let me rewrite that sine of y. And essentially, if I've got a simple function like this, all I need to do to solve for y is take the inverse, in this case, sine. And we've used this to solve equations. It works the same way in a function. That inverse sine is going to cancel the sine function. So all I've got left there is y on the right side. And I do need to apply the inverse sine to the left side as well. And that's going to give me my inverse function solved for y. Y equals inverse sine of theta. And I'll go ahead and box that, since that is half of my task, is to just write that inverse function. Now, the second half of that is to graph the inverse function. So I'm going to start off by creating a table, and we'll just assign our 2 variables, theta, which is my independent variable, and y, which is my dependent variable. And for this task, what I want to do is I want to lean on the graphing calculator. So I'm going to take the function we just wrote, and I'm going to switch over to Desmos. And let's go to the graphing calculator and find a table. So first things first, I'm going to type it in. Now, we had written it y equals inverse sine of theta. For Desmos, I want to switch over to function notation. So f of x equals, I will choose the inverse sine function from the functions tab. It's my first inverse function there. And I'm going to call theta x. So that graphs for us the picture. Let's get a table. One thing we've got to ask is, why is that graph so small? So I've got a table here, and it reflects why the situation we're seeing with the actual graph is that there's not a whole lot of points that are actually graphed here. Let's take the ones that we've got. So definitely I'm seeing -2 and +2. The 2 extremes on our table are undefined. So what we'll grab is -1, and that's -1.57. And just thinking about how this function may be set up, that is a version of pi over 2. So I'm going to write it in both ways in my table. -1.57 is pi over 2, 0 zeros on my graph, so the origin, and 1 +1.57, or pi over 2. So not a whole lot of coordinate points to find here, but let's head back to our note screen to graph our inverse sine. So I'll just recreate the table we just saw. So at -2 and +2, the function was undefined. And then our actual defined points were starting at -1 and going through +1. So -1, and we'll write it in both ways. So we saw that it's really pi over 2, which is about equal to -1.57. 0, 0 was exact, and then 1 pi over 2, that's exact. The approximation we were seeing on Desmos was 1.57. So we'll graph this, and as we graph it, we want to think, why is this function so small? So I'm going to start off, notice my x-axis is scaled like for a normal trigonometric function. So I just have to keep in view 1 is about, if I kind of track it here, it's roughly in between negative pi over 4 and negative pi over 2. So I'm just going to estimate there. And then I'm going to have to estimate as well for negative 1.57. So there's our estimate there. There's 0, 0. And here is positive 1. Again, I got to estimate that on the x-axis, and then positive 1.57. And we can go ahead and sketch this curve. Now, we're used to the sine function, which really goes infinitely to the left and the right. So if we're thinking of an inverse function, the inverse of sine, we would think would go infinitely up and infinitely down. The reason we don't include all those values is really because of the fact that if I were to include them, and I'll just put kind of a ghost version of the rest of the sine curve here, is that would not be a function. And so what we do, and Desmos does this automatically for us, is we restrict the domain of the original function so that our inverse is a function. So really all we're looking at here is the blue curve, and it's the slice of my sine function from negative pi over 2 to positive pi over 2. And we would not include the red ghost lines. We just put those there to make a case for why that graph looks like so small. It's a fragment of the original. Well, that's our first example, one of the basic trigonometric functions. We want to take a look at one of these that has had a change in the vertical translation. So here we've got the function y equals secant of theta plus 1. So what we'd expect from the original graph is this would be the secant u's that alternate one opening up, one opening down, and so forth forever. And then the whole function had been shifted up 1. So if we consider like our x-axis would be closer to the pieces of secant that are opening downward. So that's kind of like what the original would look like. Let's investigate the inverse. So what I'm going to do is accomplish that first task. I want to write the inverse function. So I'm going to take y equals secant theta plus 1, and I'm going to switch my variables. So my next step is going to read, instead of y, theta equals secant of y plus 1. Now, since there's an additional component to this function, the plus 1, I have to cancel that first before I apply inverse secant. So I'm going to write minus 1 to cancel the 1 on the right, minus 1 on the left, so that my next step is going to be theta minus 1 equals now just secant of y. So at that point, I'm ready to cancel secant by applying inverse secant. And it'll do just that on the right side. I've got to put parentheses here on the left side. And then I'll apply inverse secant. And at that point, I have a good inverse. It's going to be y equals inverse secant of theta minus 1. And again, I'm going to box it just to emphasize that's half of my answer is the actual inverse function. Just like we did with inverse sine, I want to take this to Desmos to graph. And like we did for sine, again, we want to definitely ask ourselves why the inverse graph looks as it does. So let's clear out this function that we typed in for the first inverse. Here's our next one. So we'll use similar way of writing. Instead of y, I'm going to use f of x. Instead of theta, I'm going to use x. But again, you could select inverse secant from the list, or you can just type it in. And then I'm going to put x minus 1 for my angle. And again, we have what looks to be only a fragment of the original graph. Remember, secant has infinite, what look to be like U curves or A curves across the domain. This is much restricted again. So let's investigate y by finding a table. And as we can see, this function's a little different. It continues to negative infinity on the left. It has a break here in the middle between 0 and 2. And then the whole graph continues to the far right to positive infinity. So what we want to grab, let's grab a table from -2 through 4. And I'm just going to round to the nearest hundredths. So -2 is 1.91, -1, 2.09. 0 is 3.14, which you can guess that's pi. And you can see that's the maximum value here on the graph. In fact, when I click that point, Desmos labels it 0, pi. Then we've got that gap from 0 to 2. You can see 1 is undefined there. 2 picks up at 0. So that's, in a way, that would have been the minimum on this graph, the way it's presented to us. 3 picks up at 1.05 and 4 is at 1.23. We'll take those table values back to our notes to finalize here. Let's just record that table and then we'll sketch our graph. And then, like we did with sine, we want to see what happened to the other portions of secant. So here we'll replace our actual variables, theta and y. So for us, we've taken the domain -2 through 4. And our y values were 1.91, 2.09, 3.14, or pi. 1 itself was undefined. So remember, we had that gap in the middle of the inverse function. 2 was at 0. 3 was at 1.05 and 4 was at 1.23. So let's graph that here again. So as you can see again, my x-axis is scaled for the traditional radians, and I'm just going -2 through 4. So I got to kind of keep in mind here where -2 is. Roughly speaking, I believe -2 is going to be definitely in between pi over 2 and pi. Let's just check what that intermediate 3 pi over 4 would be. So I just want to see 3 pi divided by 4. And let's do this first. And then we'll do pi times 3. And then we'll divide that by 4. Again, I'm just looking to see what's the value here on my, in fact, let's try this. 3 times pi divided by 4. So that's roughly 2. So I can see that this is about 2.36 right there. So where I'm going to pick up is, let's just estimate about here. So that's about -2. I'll just make that mark on the x-axis. And then I'm going to rise 1.91. So that, again, I got to estimate. -1. So again, if I just kind of dissect my x-axis, is about at 2.09. So just above 2. And then 0 itself is at 3.14. We've got our gap, and then again, we pick up at +2. So that's going to be a little bit less than 3 pi over 4, and that's actually at 0. 3 is at 1.05. So again, I'm going to estimate pi is exactly 3.1, well, about 3.14. So 3 is a little less than that. 3, 1.05, and 4 is going to be 1.23. So a lot of estimation as we're graphing these inverse trig ones. I'm going to place that upper curve, place the lower curve, and that's a good replication of what we saw in Desmos. Now, what we didn't see on Desmos is what happened to the rest of the graph. So just to make a case, if I had really included all of the coordinate points that are part of secant, I would have included all these curves. In fact, there would have been infinite of these red curves back and forth, left and right. So the question again is, why do I just have that purple fragment of the graph instead of the entire, what I would think of as the inverse? And just as we saw with sine, we have to restrict the domain on the original secant function here so that our inverse is actually a function. If I were to include both the purple and the red components here, that would no longer be a function, it would be a relation. And so we do again restrict down to just the parts of the inverse function that would kind of give us a picture of what the inverse is while at the same time remaining a function itself. So our second example there was involving a vertical translation of secant. Let's take a look at one final example that involves a change in period and also phase shift. So here I've got y equals tangent of 2 theta plus pi over 6. I want to start off the same way by writing the inverse function. So we'll put the original first, tangent of parentheses. Now I got to mind the parentheses here, 2 theta plus pi over 6. I just got to keep in mind 2 theta plus pi over 6 is altogether the angle. We'll make our first step. So I'm going to switch the variables. Instead of y, I'm going to write theta. Leave a space there, just anticipating inverse tangent, and 2 instead of theta, y plus pi over 6. And at that point, we are ready to apply inverse tangent. So like we've seen on our previous 2 examples, that'll cancel the trig function. It'll show up on the other side. And then what we've got at that point is going to be inverse tangent of theta equals 2y plus pi over 6. So now my goal, it's changed a bit. I just want to solve for y. So I've got 2 and I got pi over 6. The first of those that I want to move is the pi over 6. I'll cancel that by subtraction. Now I got to be careful. That pi over 6 was on the inside of the angle in the original function, but now it's not. It's in a way a vertical translation. So my next step, I got to kind of note that it's inverse tangent of theta. And I'll just put parentheses to say that is my angle. Minus pi over 6 is on the outside of the angle. And on the right side now, all we've got is 2y. And my goal is to solve for y at this point. So I got to cancel 2. And I'm going to do that by multiplying by half. You could also divide by 2. It's going to cancel that 2 on the y in any case. And that gives me my inverse function. Y equals 1/2 times inverse tangent of theta. And I'll put those parentheses minus pi over 6. Close parentheses. And I will box that. Again, that's half my answer is the actual inverse equation. So to get our graph, what I'd like to do is again, head to Desmos. Desmos does a nice job of restricting the domain of inverse trig functions for us. So all I'm going to do is I'm going to clear out this old notation from our inverse secant. Let's type in this inverse tangent. So it's half parentheses inverse tangent parentheses. I'm calling theta x here. Again, that helps with my table, right? Table creation here on Desmos. Minus pi divided by 6. And there's my graph. Picks it up just right. So again, I want to get a table. And definitely the inverse tangent, we can see how it's the tangent graph turned on its side. So the left side is infinite towards negative infinity. The right side's infinite towards positive infinity. So I'm going to just pick up this exact table that we got. I'm just going to round to the nearest hundredth. So -2, I'm going to pick the point -0.81, actually 82. -1's -0.65, 0 is -0.26, 1 is 0.13, 2 is 0.29. One thing I want to note, this has a very similar look to the cube root function, but it's different from cube root. If you remember, cube root doesn't have any restrictions in its range. It goes from negative infinity to positive infinity. But tangent's different. If you remember, the original tangent had vertical asymptotes. So if I'm thinking of an inverse, it means I've got horizontal asymptotes. And those actually bound the graph from below and above. So I can find those. The usual ones would be -pi/2 and pi/2. Now, if I just type in -pi/2, you can see that that's way lower than my actual graph. It's because I've also got a phase shift here, and I've got a change in period. So using that half and the pi/6 that I see in my equation, that's pi/12. So what I want to include is that scaling. So it's -pi/2. In fact, what I'm going to do is I'm going to take care of the phase shift, or the period adjustment, by multiplying by half. So pi/4, -pi/4 minus pi over, instead of 6, I got to multiply denominator by 2, pi/12. And you can see that that lower asymptote really does follow that curve, and the curve won't ever go below that line. We can also find the upper asymptotes at pi/4 minus pi/12. And that appears with that red one. So different from the cube root function, this is a sandwiched function. It does not go above that red line. It does not go below that black line. Well, that's more than enough to graph our function. So let's head back to finalize this graph. Let me just recreate that table for us. So again, we'll put theta and y. And remember, we had picked up -2 through +2. So we'll replicate those 5. And then our outputs were -0.82, -0.65, -0.26, 0.13, and 0.29. So again, let's place these. We just saw with our previous example that 3 pi/4, so that value in between -pi and -pi/2, that's a little more than -2, a little less than -2 if we're thinking negative. So -2 itself is going to be somewhere here, down -0.82. -1, we'll say, is about here, and that's down 0.65. 0's just below, about a quarter below. And 1 is 0.3, 0.13. And 2, again, a little less than 3 pi over 4 is going to be 0.29, about a third. And here's our function. So we'll sketch it in. So we got our original, well, our inverse there with a red curve. Again, the question is, where's the rest of the tangents? Well, same problem that we saw with the first ones. The rest of these tangent values are actually here. It's just we've restricted the domain of the original, because if I were to include all these other tangent parts, kind of reiterations of the function, clearly that's no longer a function. And so again, kind of we keep in mind that these blue reiterations are here. It's just we restrict them and only take the red one so that our inverse is actually a function. Thank you for joining for these 3 examples looking at writing and graphing inverse trigonometric functions. See you soon.